Welcome to this third colloquium of 2025. And as you can see, it's devoted to computer science and modern developments thereof. The next colloquium will be on April 9th, and it will be devoted to theoretical particle physics. Then you will get an announcement in due time. Now, my colleague Fabio Bertrand will introduce the speaker.
Thank you very much, Augusto. Thank you all for being here. A special thank, of course, to our speaker today, Alessandro Curioni. Thank you very much for being with us. Normally, I should start by giving all the long list of his responsibilities and titles within IBM, but what I prefer to mention first of all, as a first thing, is that he is a former student of Scuola Normale. As a matter of fact, he did here both his undergraduate studies and graduate studies with a PhD in theoretical chemistry. He, in some undetermined time in the 90s, because I don't want to give him his age, some point in the 90s he got his PhD here. Already during his PhD, he visited IBM, but he is a permanent person there since 1997, which kind of puts in a date frame. His scientific interest now, as you probably all know, is on high-power computing and with an accent, I would say, on novel paradigms like quantum computing and artificial intelligence, which are the topic of this colloquium. We have been after him for some time, and it is quite a privilege to have him here. You can imagine that this is not a simple moment for a VP of IBM to be available for a scientific talk with what's happening in the United States and the rest of the world as a consequence. So we are very thankful that you made it here. This talk is very close to some of the scientific interests of Scuola Normale too. Not only did Alessandro Curioni's interests evolve in this direction from his original PhD in chemistry, but also Scuola Normale with an interest in data science, artificial intelligence, and quantum computing, which are important aspects of our faculty and interests in many of our students. So Alessandro, thank you very much once again for being here. The floor is yours. Thank you.
Thank you, Fabio, for the introduction, and thank you very much to Scuola Normale for inviting me here. Yes, indeed, it's more than 30 years, right, when I started here as a student. And this place was home, literally was home for me, because at the time I was living in this building for around 10 years of my life. Yeah. So then I went completely different directions, continued to do research for many years, up to when I decided that I could have probably impacted more both science and research, trying to develop strategies and leading people, yeah, and that is where I am now. But I will be always thankful to this place because it didn't only prepare me for the basis of whatever I have done, but also gave me, you know, this critical thinking, open minds to problems that, in my opinion, is the most fundamental thing that one should have, can have, or could have as a researcher, but especially as a human being these days. So what I'm going to tell you during my presentation, it's a couple of things. One is that science and whatever we are doing to enhance our knowledge, okay, have a strong importance per se, but they have also a very strong importance because, especially today, science and knowledge could be the base of the solution of most of the problems that our world has. Okay? So the base and increasing knowledge, to me, is a right of the human species, like the right of speech, the right of freedom, right? But the ability to use all this knowledge and try to make a difference, to solve a problem so that everybody can live longer, better, and with a better quality of life is also an important part. And second point, science has always, let's say, progressed thanks to people, but also thanks to the instruments that people had in their own hands, right, to push this progress. So new instruments accelerated science and accelerated always the impact of science, as I will show to you. The third thing is that we are going through this decade, unfortunately not when I studied, but these years, 2020s, is a decade in which we are going to have two of the largest transformation in information technology. That has been one instrument for science, but the transformation that are happening today are going to create new instruments that I will discuss with you that will, I will not only accelerate, but will transform the way we create knowledge, we manage knowledge, and we use knowledge to solve problems, right? So this is a slide that you know, I put together a couple of years ago when we were in COVID. And at the time, I was asking myself and say, come on, you have been studying for all these years, you spent night and days to try to push what I was doing, that was computational science. And in spite of this, every time there is a new virus, a new bacteria, or every time you have something happening in the earth, an earthquake, right? Anytime there is a problem, we don't have solution for most of these problems. We don't have solution for pandemics. We don't have solution for climate change. We don't understand fully climate change. And what we understand, we cannot act on it. We don't have solution for hunger. We don't have solution for overpopulation. We don't have solution of most of the bigger problems. So you can say this is something that is not, should not be the goal of a scientist. It should be the goal of the politician. But I tell you that if you take away the scientific thinking and the method and the science from political decision making, this is a recipes for failures, and we have seen it, right? So, do one step back. I was telling you that science can be the base of a solution of most of these problems, but science per se, you know, is a concept. The most important instrument, I put this in this way, or that I don't call an instrument, methods that is at the base of science, is the experimental scientific methods that in the years evolved a lot, but the methods remained always the same. You have a problem, you try to solve it. The first things that you have to do is to understand your problem, so you gather knowledge or enhance the knowledge, right? You use this knowledge to formulate hypotheses, and then when you have the hypothesis, you can create theories to try to confirm the hypothesis and go to a larger scale, but at the end you have to go back to the real world and test your hypothesis or your theory. Depending on this, you know, you do one step forward and you iterate up to when you have the solution. This method is probably the most strongest method and solid methods that we do have, but there's only one problem, that is very slow, it requires a lot of iteration, and has problems to deal with complexity overall, okay? So, should be the base of whatever decision we take, but it's not so effective or efficient. And by the way, in spite of these different stages with different methods, you know that the adoption of the scientific methods was not always immediate and not easy. So there are several, and some, of course, also that we know very well, example of situation in which scientists have used the scientific methods. They even done experiments on their own self to demonstrate something, but it didn't go so well, right? But in spite of this, the method worked. And we also know, as I was telling you before, that the evolution of these methods has not been, let's say, evolutionary, but it went through discontinuities. And most of the discontinuities were coming from having new instruments. Every time we had a new instrument to observe the world, okay, or to test the world, or to manipulate the world, yeah, to close that loop, we made step forwards. Think about the microscope, the telescope, the accelerators, right? So they are all new instruments. What happened a few years ago, decades ago? We had, fundamentally, at a certain point, a new method that was the computer, information technology, okay? And at that time, if you look at the acceleration of science, all the fields, medicine, chemistry, physics, astrophysics, theoretical physics, everything got accelerated thanks to information technology. And one thing that information technology allow us to do is to create this new realm that is called computational sciences, in which you take the knowledge that you represent it in a certain way using mathematics. In most of the cases, differential equation. You take that, you discretize that, you put on a computer, and you can try to simulate on the computer part of the real world. Yeah? And that is what computational science has done. And there were several significant examples of successes of computational sciences, right? Think about, the first nuclear physics simulation, 1945, or the ability in cancer research to simulate at the system biology levels, complex or relatively complex objects to do drug discovery. That are definitely examples that tells you new methods applied to science helped to do step forward in science and have also an impact to the real world. But there is one problem, and that is one of the key messages that I want to push to you, and people are speaking about that, but I don't believe that they are really entering at the core of the problem. What is stopping now us to use all these new methods, including computational science, to really try to solve the problems that we care a lot, yeah, in science and eventually the application of science? Is one thing that has a different face, is complexity, okay? You have different way of complexity. One complexity is the computational complexity. You can have problems that when you represent the problems using a certain representation, and then you try to discretize and you put on a computer, the amount of computing power that you have to put in to solve the problem scales exponentially or combinatorially with the problem size. Okay? What does it mean? It means that you can simulate something, but when you go to something that makes sense to the real world, you cannot do it because you need too much computational power, and if it's exponentially combinatorially, you know that there is nothing that you can do to fight an exponential, yeah, with a linear increase of resources. It's practically impossible. The other things, it's the complexity that come of having to deal with what are called in physics complex systems, or systems that are made by many different subunits, being atom molecules, but can be everything else, right? And the behavior of the system doesn't depend on the single units, but depends on the units and how they interact one with the others. So it's almost impossible to deal with these systems, right, if you try to understand and simulate from the basic constitutional units. You need to do big approximation, or you have to hope that something emerge from complexity, yeah? So, and in many cases, something emerges from complexity, so you go from something that is very complex, and then you can treat in a much more simple way. But in many other cases, this is not visible, or is not there. So, having the ability to try to to reduce the computational complexity problem when you go down, to the simulation from first principle, and the other side, to deal with these complex system behaviors, is what we need to do and we need to tackle if we want to do the next step. And next step would be to use information technology to try to make a difference. I give you an example. There were people, and still people in this world, that do believe that indeed, if you are clever enough with what you know and with the limitation of our brain, of our knowledge, you can tame some of this complexity, right, by hand. Yes? Human Brain Project, 600 million investment was thought, through simulations, okay, to understand how the brain works and cure stuff. I would not say has been a huge failure because it pushed the knowledge forward, but it didn't solve the problem at all. Yeah, so that is one example going in this direction. Problem is that if you want to do things accurate and bring back to the constituents, okay, then with the representation that we do have today, complexity kill you, you will never be able to do it. If you want to approximate, you can approximate, but in many cases, if you don't get the right emerging behavior, you approximate the wrong stuff. That is what is happening. So there is one thing, as I was telling you, that is happening these days. Two major transformation in information technology, in my opinion, are the largest one in the past 30 years. And if you tell me, Alessandro, go back at the beginning, are there similar transformative change in technology? I would say that I can find other two only. One, the invention of the transistor. Yeah, computing was very restricted, it went everywhere. And then after a couple of decades, internet. Once you have computing everywhere, you connect them, and then you create a super system that is much more powerful. Two, hyper-transformation. All the rest has been an evolution. Think about cloud computing, it's an evolution. Yeah? Think about the mobile, it's an evolution. It's all evolutions. And the difference is that what is happening now, these two transformations are happening at the same time. And why I'm telling you this? Because if you do have two transformative changes in technology, especially in IT, that are happening at the same time, you know the impact of one, eventually, the impact of the second, but the synergy of the two is much more difficult to be understood before they get to maturity. So give additional opportunity. I do believe that this is going to impact scientific discovery and the society. Which are the two big transformations? One is the new artificial intelligence, and I will spend a couple of minutes to tell you why the new artificial intelligence. And I do believe that the new artificial intelligence, especially the self-supervised models based on transformers-like architecture, are going to help us to tame the complexity that comes from the different scenarios. Because it will help us to analyzing simply data that are measured to understand which is the best representation that emerge. Okay, one. The second one is quantum computing, because quantum computing, not for everything, okay, but for certain type of application that, by the way, are the ones that are very interesting for us, is going to tame the problem of computational complexity scaling. Okay, so we do have these two new instruments that are transformational and are not only transformational, are really focusing on trying to solve some of these big complexity problems that I was telling you before. By the way, this is my beliefs, is something that I'm pushing like crazy. I believe that I'm very right? Maybe I'm wrong, but we'll see with time, and maybe we can have another presentation. Why AI, this new AI, it's, as I told you, is transformational. You can tell me, Alessandro, we are speaking about machine learning and artificial intelligence since 50 years. Every time there is somebody that says this is going to change the world, we are going to now to generalize artificial intelligence, blah, 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 blah. But at the end, nothing changed. Or as only the impact is relatively small. The difference from the old world to the new one, it's not the fact that we do have generative models, by the way. We had already generative models before. It's the fact that today, thanks to the invention of this transformer architecture, okay, and the ability to do self-supervised learning on this architecture, we can learn directly models and the best representation from the data without the need to do any or a lot of human annotation, human intervention. That is fundamental for two reasons. One, it makes the return of investment of artificial intelligence much higher. If I have to create a model to solve a specific problem and solve only that problem, and I have to put in 100 people to do annotation of the data, you know, it pays only if the problem that I'm solving go to scale, face recognition in the airport. But for most of the other, it doesn't. The second thing is that since I am learning from data, modeling the best representation that emerge, that allow me to understand and discover connection between multimodal data that you will not be able to understand without doing this thing at all. You can apply any other statistical, cross-statistical method, you will not be able to see. Or if you will be able to see, you will need to do 100 years of data campaign and work and refinement. This is all, almost all, machine-driven, okay? Yeah, this is exactly right. The supervised learning that we had before, human power, a lot of labeling, long, hard, and expensive. This one is computer power, no labeling, quick, automated, and efficient. And what allow you to do is instead to have as a beginning different problems, different models, and different solutions, you create a model directly from the data. You can integrate one modality, but you can have more modalities, right? Once you have created this model, you can use the model itself with a little bit more data to specialize and create smaller models that do what you want to do. But this big model become your best representation of the knowledge in a certain field. The data that were before, I don't say, sometimes I say you can throw it away, but almost you can throw it away, because once you transfer the data, the knowledge in the data, from the data to the model, the value of the data, the knowledge in the model that is fully connected is much higher than the value of the data before, right? So, and analyzing these new models and analyzing how the data are represented allow you to understand also more. And I will tell you why and how these impact science and scientific discovery. There are different strategies on how to do these things, right? You can think, and it depends what you want to do. If you are oriented to the outcome, the usage of the model, you don't need to do this a super large scale and integrate everything, because some of the connections are already clear. And it's true, you delegate this to machines that are more efficient, right? If you are interested instead to understand the connection and new representation, then yes, you have to go to larger scale and then analyze the stuff, and that is more expensive. But again, you go from something that we as a human, we will not be able to do, to something that you can do, okay? And then it's your decision. It makes sense to do, to invest, the return of what I invest is large, or I could do this with a simple regression and go to hell, right? So another important thing, what you have seen with the big language models was all based on language and text. But the same technology, the same vision and thinking can be applied to any data structure that is not random. Yeah? So if you have a data structure that comes from the way you store knowledge, sensory in an experiment, results of a simulation, that of course is not white noise, is not random, right? You can take it and create foundational models that are modality specific and field specific in that way. So that is valid for text, for speech, for images, for codes, for the language of science, etc., etc. And that, by the way, is what we, and myself, by the way, in IBM, I've been pushing in the past couple of years, where everybody was pushing to try to get only the largest possible big language model, to come up with foundation models for this specific usage, okay, that can be used as an initial sort of knowledge data for all the possible downstream tasks. Which are the models that we started to create? Of course, these require collaboration, data, compute, geospatial satellite analysis, collaboration with NASA. The language of life science and healthcare. You can create biomolecular foundation model for healthcare. Materials, laboratory workflows, cybersecurity, etc., etc. Okay? So these models, as we were saying before, you don't integrate everything. The latency is really amazing. But you integrate only the data for that modalities or for the couple of modalities that are useful for what you want to do. But everything else is automated. I want to give you an example because this is something that we have been working indeed since 2016. 2017 is where the transformer architecture came out. We were working on this already in 2016 using standard deep learning models where we added by end what is called a couple of attention layers that are, this layer in the network that today are the base of the transformers. The transformers are a series of subunits, each of that with these attention layers at scale, okay? These attention layers, what they are doing? When you have data, they allow you to understand which of the data is more important for the outcome you are interested on, where to focus the attention, right, when you learn, and the connection between the different data in a series, okay? Doing that, we were able to take organic chemistry. I am a theoretical chemist, and I was forced to study organic chemistry for 3 years during university. Was the most, there is no organic chemistry here, I hope, the most annoying thing that you can do. Because, yes, there are rules, but are very, very empirical. It's a lot of memorizing, etc., etc. And then, even the best organic chemistry, if I tell you, put together these 4 molecules, what is the results? They are not able to tell you in 2 seconds, yeah? We trained a model starting only from existing published organic chemistry reactions. By the way, we have taken the collection out of patents, not scientific papers, because the patents they were much better and more accurate than the scientific paper, open, close, okay? And we have used it to train. The first was a deep learning model with attention, now a transformer, that is able to predict the outcome of chemical reaction, organic chemical reaction, with an accuracy of 90-95%, depending on the class of molecules. Once you are able to do it, you can invert the problem. You can say, I write a molecule on the screen, and I ask the machine, tell me which is the best recipe to synthesize this molecule. And the machine automatically come up not only with the molecules that you have to put together, but the real recipes. Put these things together, heat up at 200 degrees, put this stuff, and blah, blah, blah. So you come with a recipe like this that then you can take, and we have done. You can interface it with a chemical robotic lab. So here you have your molecules, right? He does all the stuff, and then step by step, he runs the synthesis in a completely autonomous way. I don't know if you can see something, yes? In a completely autonomous way. So in other ways, we have got to the ability to digitize an industry, like the chemical industry, that is one of the most legacy-oriented industry. Okay? And once you have done it, imagine, you can do the creation here at Scuola Normale, and you have the robot in the Sahara Desert, right, in a super safe place that is doing all the synthesis, and then it's done. We are now taking these things and bringing, as a part of the next Artemis NASA ESA missions, on the space, so that you can do the synthesis of what is needed on the space with few reactive that you put us directly from here up in the space. So the fabrication and the ideation is completely separated. That, you know, if you come from that, is really a big step forward. Again, that was initial things. What we are doing now, we created, starting from different representation. You see there, you have chemical formulas in terms of smites, graphs, 3D position, electron density, test description, all the properties that you can have, and the connection. You create a models, that is a foundation models, that connect all these modalities, and then you can use it, you know, you can ask the model, can you tell me which are the 10 best molecules that you know that have a boiling point larger than X? So if you do this in ChatGPT, it gives an answer. But this answer, 99% is fully hallucinated. Because, of course, a recipe for that model is a kitchen recipe, is a chemical recipe, is anything, right? If you do like this, you get to 90-95% accuracy in the answers, okay? That is for chemistry, materials, and these models we create, we put out in the open, because we want people to use and contribute. And, you know, there are already different versions with different tune version to predict polymer formulation, blah, 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 etc., etc. So it's a reality, you know. A big change, it will take time for people to follow, but it's a different way to do research. Same thing is for life science. You have all these different modalities that they were analyzed, you know, with all the system biology, blah, 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 in a manual way, with loops and so on. You don't know anything. You take, you integrate, you come up with a model, a merge representation, then you can take some of your data that maybe a pharma has. This one is done at the university, this one is done in the industry, and then you interrogate your models and come up, for example, with a list of new antibody for certain stuff. And again, open, because you want this to become the next way we are doing science, okay? I was telling you before that any fields of science, you can apply this type of things. And I will show to you that we do also stuff on high energy physics and other, even on the theoretical side of science. Here, one of the applications that probably is giving the largest impact and will give the largest impact are these geospatial foundation models on satellite images. You know satellite images? There are already an enormous amount of them with timestamps, with different type of images, infrared, etc., etc. And most of these, by the way, are open. Yeah? You ask yourself why all this value is all open. The reason is because many people have tried to monetize this, but the monetization was not easy, okay? So now with this new technology, you can take and you can create multi-models that allow you on the same images to look at the heat distribution, the crop distribution, the burn scales, floods, land use and change, ground, everything. You know, if you have enough data and they have enough overlap between the different modalities, you can ask almost everything you want. And one of the things that, by the way, we have been starting to do in different places, but we have a project that I do hope that with all the, how you say it, the speed that we do have sometimes in places, also in Italy, is going to happen. But using these foundation models to try to predict hydrogeological risks. And we have one of these that I want to show to you. Let's see if it works. So, look, that is what I wanted to show to you. But this is north of Italy. It's a place where there was landslides, okay? And using the foundation models, we could, let's see if it works or not, indication where, this landslide was starting, and once you know that that is a starting, you can use and ask the model, tell me the other places in Italy where you have the same type of feature. And then eventually to go down and identify all the places, the houses where that would be impacted by that type of landslide, right? Okay. And as I was telling you before, all this is becoming a reality, and what we are doing these days is to create a worldwide alliance that is called AI Alliance. We started 1 year ago, 2 years ago, and with 50 members. So now you see you have 150 members. There are universities, there are research centers, there are companies, etc., etc. And the goal of this one is to develop these basic foundation models in different fields in an open and transparent way. Because for us, it's the only way to get and bring credibility on this type of AI. And on the other hand, it's the only way to make sure what you were saying before, if everybody, as it was happening, is happening also now, start to create his own models based on the same data, you throw away a lot of money, a lot of resources, to get, at the end, to the same stuff. Or less, yes? So crazy. Okay, that said, let's accelerate and do the last part of my presentation. That is about, it's really very slow, my God. It's the speed of the light. Anyway, it's quantum, okay? So why quantum? And I think that this audience, most of you probably, I don't have to explain, this was I was doing 10 minutes ago, but that is okay. Come on. So, why quantum? Yeah, it's relatively easy to explain. Whatever we have done so far in computing has used a way to represent information, and everything was based on this way, classical information theory, everything is in 0 and 1, etc., etc. If you take reality, if you take differential equations, if you take anything that you want to represent with this 0 and 1, you have problems where the representations, right, scale linear or polynomial with the size of what you want to simulate. Others where, as I was telling you before, scale exponentially or combinatorially. It's not a problem the classical computer is bad. It's simply that the representation that you are using to compute on that type of problem data is not the right one. That is a base. That is what quantum computing allows you to do. It extends the class of problems that you can study with a computational complexity that is reasonable. Should not be linear, right? It can be even polynomial, but is reasonable, is not exponential. And by the way, the very important thing is that people don't get fully is that what a quantum computer is able to do very well, a classical computer very probably is not able to do very well, and vice versa. If I want to multiply two numbers on a classical computer, super fast. If I want to factorize one number, it's super slow, right, when I increase the size. Quantum computer is the other way around. If you want to do a simple 64-bit multiplication, it requires a lot of time. If you wanted to do the factorization, it's very fast, okay? Why this is important? Because this new way to do computing will allow to do things that we could not do before. It's not simply doing things that we were able to do faster, but new things. And you can tell me, Alessandro, yes, but who cares? If the new things is to simulate an icing model, yes, it's very nice, but at the end I'm not going to change the world, right? But if new things is going a step further, simulating nature, what I was telling you before, chemistry, biology, material science, etc. If the problems that allow you to do better and lower complexity is global optimization, come on. Global optimization, I do things 1% faster, 1% better, more accurate in certain fields. It's like day and night, okay? The one that everybody, why everybody is investing on that really is for finance. Yes, 1% in portfolio stocks better, you push everybody out of business, right? But the third one, that is what I was telling you before, is the interaction between quantum computing and machine learning. So the analysis of small, not big, because bringing data to a quantum computer is very difficult, but small, but very intricate set of data, so where there is something hidden that happens only once, right, very rare, is probably what a quantum computer is able to do much better. That a standard statistical approach like machine learning and AI is not able to do. That is statistic. In order to be able to take out something, this has to happen many times. If it happens only once, and you can imagine, think about factorization of a number. Factorization of a number, you can even think to find, like if you want to find a structure that is hidden in the number that you don't see when you look at the number. That is factorization, right? You have the two, you don't see it, you multiply. So same things in small but complex data set, they could make a difference. The very interesting thing is also that in the past 5, 6, 7 years, the evolution of the base technology around quantum computers has been really huge. We started 7, 8 years ago, we had qubits. We were using superconducting qubits, but qubits that had error rate of 1/10. So you do 10 operation, right? And you look at if the results is 0, 1, was giving a wrong results 1/10. Almost unusable, right? To now that we are very near to 1/10,000. So you can have 10,000 operation on the single state, right, on the same state and the sum of states, and still have the machine working in the right way. And it's not only to have a device that works. What we do have these days is a full roadmap. And why I'm telling this to you, you are not technologists, or most of you are not technologists, but if you want to understand if a technology is real, the only question that you have to ask to the technology is, what is your roadmap? If it tells you, yes, we have 32, but eventually maybe we know that we can go to 100, forget it, right? If somebody tells you we have 30, we had 16, we have done 32, we have 64, we have 128, we are going to have 1,000, and then 100,000, 1 million, and you can demonstrate that happened in the past, then is when the technology become real. So that is why we do say it's not only that we have quantum processor unique with 130 plus qubits, with 10 to minus 4 error, with that topology. We do know that in a certain amount of time, we do know that we are going to get to 100,000 qubits, 1 million qubits, so to have a machine that will be able, and when I say qubit, I am referring now to error-corrected qubits, right? So virtual qubits, a machine that will be able really to do things that are transformational. So I was telling you before the free class. So simulating the nature. Yeah, what we can do already now with a quantum computer, okay, is to start to simulate small molecules, okay. The thing that I wanted to tell you, you can ask, we have the technology now, end of the decade, we will have, the error-corrected one, right? And complexity, simulation cost, this is linear, the quantum computer fully error-corrected, this is the classical one. This is what we can do today. So we are not error-corrected, but we can mitigate the error. So the scaling is still exponential, right? Because you are not able to have a real, full digital quantum computing, but it's a slower exponential. So you can get already value today with the architecture that we have today. So what does it mean? You can simulate already start. Stop.
Recording in progress.
Interacting with the scientific community in different fields, and I will share the presentation. We have white papers in which we have done the detailed analysis on what we can do today, what we will be able to do in 2030 in selective fields that you see here, right? So healthcare, life science, mainly is drug discovery, high energy physics, okay? We are collaborating with CERN and others to see how this quantum machine learning could be more effective than the standard one to find the rare events, materials, and eventually optimizations. Okay, so this is real. It's not only speaking. In simulating the molecules, what you do now is to do what we were doing. Quantum classical approaches in the past with density functional theory. You do it simulating the active size or the molecule you are interested on the quantum computers, and the rest classical. With CERN, as I told you, you see quantum machine learning algorithm to get rare events, for example, the scattering events, or trying to understand this. It's is in the early phase. If you could help us to solve also or to tackle some of these theoretical problems. In the field of life sciences, this is with Cleveland Clinic. You remember drugs to cure diseases for the full population? We went to personalized medicine. So now we do believe that using quantum computing plus AI, we can do cell-based therapeutics. So in other words, I don't cure yourself, but I cure your tissues. Eventually, maybe you have cancer with this heterogeneity, because I get a therapy for each of the part of the tumor that you do have that usually you don't. So if you get all these, and I go back to what I was telling before, I am accelerating because I lost a lot of time, taking that technologies and applying to the different part of the scientific method, we know that we can get a factor 1,000 for knowledge ingestion. You take PDF of papers, you take it in, you structure, you can ingest directly to create, the foundation models that I was telling you before. You can use quantum plus AI to eventually augment this knowledge. Imagine in drug discovery, I have a certain property for 90% of the molecules, I need the other 10%, and these other properties on a classical computer with classical algorithms are not accurate enough. I use quantum, so I have accurate knowledge, right? It's faster and more accurate. So then, once I have the generative models, I can use it to generate hypotheses, and then I do the testing. In the case of material discovery, we have created these technologies, and it's all open, right? There are toolkit for knowledge ingestion, for simulation, for generative AI, and the one that you have shown for chemistry for testing. So in principle, My God. So, ok, inizio a pensare male. The reality is that I really do believe that after all, the evolution of science, from empiric, theoretical, computational, data-driven, we enter this new era that I call it of accelerated discovery, thanks to these two instruments that I was telling you before. But I would like to go back to you, to what I was telling you before, and before closing. If you have followed, unfortunately, it was not so easy because all the break inside. Most of the things that I was telling to you was about outcomes. So I create this new instrument. I use this new instrument that allow me to accelerate the scientific methods. I design better materials, I analyze better the data, etc., etc. But the question is it only about outcome what this revolution brings? Outcome in that sense. To me, we have a huge opportunity to use the tools to find and understand better theoretical, put in this way, representations of the problem that we want to study. Whatever we are doing today is basic law, continuous mathematics, differential equation, computation, simulations. Eventually, if you go on the large scale, emerging behaviors, right? Like you do with thermodynamics. But you start with the same representation of the basic things of a system. I do believe that that is good, has evolved for thousands of years, but it is, nobody is telling us that that is really the best possible representation of our world. Definitely is the best one for our brain, because that is the way we rationalize our world. But our brain is super good, but is also very limited. So that is why I do believe that take a very complex problems like battery, electric storage devices, right? The one that we do have in the telephone, in the cars, that are super complex devices. Because inside these devices, you have chemistry, you have electrochemistry, you have diffusion, you have fluid dynamics, you have heat waves, you have everything you can, different phases, change of phases, heterogeneity, everything you can imagine of physics and chemistry and of complex is in this device. If you try to understand this device, going back to ab initio, and when I say ab initio means not quantum, but really from first principle, right? You will never be able to fully understand, to better design, and to connect, initial design and process condition to outcome. It's too complex, yeah? If you, and that is what we are doing these days, creating foundation models based on time series in space, you can come up with a representation of your device that connect input parameters to outcome, okay? And connect these input parameters to outcome in a very, very, okay, so this is not working, but is in a very, very, very accurate way. So in this plot that you don't see, there was the experimental discharge of this battery and the simulated using the digital twin built with foundation model and data. The error in time is less than 1%, and you are able to extrapolate results of 500 cycles of the battery with training of only 25 cycles, okay? And you can correlate design parameter and process condition to final outcome. If you go back to the model and you analyze the internal structure of the models, what you have on these attention layers, how the neural network is done, you will be able to understand the reason why this parameter connect to the end, and what is, if exists, that is emerging from this complex device. So I do believe that doing more things like this will get us probably to understand better our world, right? And eventually come up also with new idea to represent certain part of chemistry, certain part of physics. I even saying, probably going back and putting question mark on the base of what we are doing. Simply because the machine is able to do things that they look to us, eventually people are telling me when you do this type of thing, but this is a black box. Yeah, thank you very much. Also experiments are black boxes. If you use the experiment in the right way, you can take out a lot of understanding that allow you eventually to come up with a model that is a better representation of the reality of what we do have today. We have done this in this case, but I have done this also in trying to study very complex fluid dynamics. And compare with the results of Navier-Stokes. You get the same accuracy than direct simulations at 1/50 of the cost. And when you analyze the representation, you are able to understand in which regime, for example, of turbulence, you should have worked, right? And you didn't because you started with the wrong model. So there is all these things that indeed is possible and is going to, in my opinion, if we are clever enough, and we are clever enough to use this model, will allow us to not only use as engineering methods, but also a way to do better science. And I close simply saying the last thing, all the applications that I show so far are connected in a way or the other to hard sciences, right? But these are instruments for all types of sciences. I had one last example that was application of our geospatial technologies to archaeology. That you can see how you can use, the geospatial to impact archaeology. We were able to use this technology to help the discovery of these geoglyphs. These are the structures that were designing thousands and thousands of years ago in the ground by Incas, by different population. And if you look, the archaeologists that were working on that field, they were able to find a new structure every several weeks or months, so 10 per year. With this one, with single use of the technology, we found additional 300. So we went to 10 per year to several hundred with a single application of the technology. And you are not only able to find these geoglyphs, you are able to correlate where they are to try to give a reason why these guys, they were spending time to do this picture, something that was very difficult to do in the past. Sorry, I got a little bit late, and sorry for all the problems. I hope that I was able to communicate not only my passion, but the fact that we are entering a new world. And thank you very much.
The microphone works, okay? So thank you very much, Alessandro, for this broad and exciting vision. We have still a little bit of time for comments or questions from the audience. So please go ahead, just raise your hands and I'll give you an opportunity. If you want to start, Augusto, go ahead. Vai, Augusto.
Every technological revolution had its dark aspects. No? For instance, think of technological revolutions of the 19th century. brought to the weapons that shattered the world in the First World War and then of the consequences. People sometimes talk about dangers of artificial intelligence. I think it's inevitable for the revolution, but maybe you can give a comment.
Yeah. No, senza microfono. Ah, qui. No, sono completamente d'accordo, è sempre stato così. Sorry. Yes, I am agreeing 100%. It has always been like that. And by the way, the difference is that the amount of transformative power that the new technology that we bring in the world have increased enormously. So the problem was always there. You can use it for the good or for the bad. Problem that we have additionally now is that the power is higher, so the good is much better and the bad can be much worse. But we have to use critical thinking when we analyze this problem. We do have technologies and way to do it. Not with static regulation, because static regulation in this field doesn't help, but having some sort of clever dynamic governance that look at the regression, look at the results, put the right guardrails, is something that one can do. So we have way to control that. But we have to to be very careful and not to let us, to follow the way of these Hollywood movies type of narratives in which we are going to have AGI and then AGI is going to change everything. To me, that is only a way to take away the focus on the real danger. Why? First, humanity, but also yourself, probably, each of us, when you develop new things, you would like to develop new things to be able to do better something, or to be able to do something that you are not able to do. We had the bicycle, because if you run, you are too slow. With the wheels and the bicycle, you go faster. Yes, you are a Superman in moving on the bicycle with respect to when you walk. And that's always been like this. Why the hell now we should focus to try to do something that mimic our brain, that is very good, but has a lot of problems, instead to try to do something that superpower our brain. So that is why, my opinion, these AGI things, is a nonsense, trying simply to see if we can do it, because we don't gain anything. As a man, society, as a person, I don't want to have somebody that has all the problem that I do have. I would like to have somebody that is much better than me. Yeah, allow me to read faster, understand faster. You get that, right? But this narrative take away the focus on the big problems that there are today. For example, one big problem that nobody is speaking about, or only a little bit, is the fact that most of this new AI-driven technology are going to limit enormously our freedom with time. But not our freedom, our freedom of thought. Why? Take example, recommender systems. Netflix, okay? You look a movie, watch a movie. If you like this movie, Netflix next time is going to propose you a movie that is very similar to the one that you have seen. The time after, again. What happened to you? This circle push a feedback loop that is a feedback loop of the pleasure. Yeah, it's a very well biochemically described. That is going to push you to redo things that you like. We do sex because we need to reproduce ourselves. We like eating because if we don't eat, you die. We like power because if you have to fight with somebody else and you are not strong enough, you die. So evolution brought us to get pleasure on things that are good, that we like. But these stimulus, you know, are not very frequent in time. And these recommender systems, they are going to amplify the stimulus. So with time, what is going to happen is that if you have to choose a movie, even without the recommender system, you are going to choose that movie. Because that is the one that has been amplified enormously in the feedback loop. So you lose the freedom of choice. You know, this is, to me, it's the largest possible fear that we should have. Nobody's speaking about that. Everybody's speaking about AGI and the fact that the machine will take over the people and that. You understand? Yeah?
There are significant political implications there.
Yeah, my question is somehow correlated to this, but it's less political than everyone asked. It's more based on the data itself. In the model presented of development combining the two powers, on one side there's this implication, or that I understood, that the machine themselves, unsupervised, can read the data from the data that are provided, or maybe the data they can find in the world, they can then derive theories or undiscovered. I mean, okay.
Yes.
They can try to find correlations that
Yes.
it's not possible to find otherwise. I mean, it's very difficult for us to find.
Yeah.
My, not doubt, but concern then how it is tackled in a company is how biases in the data that the machine can access or that we present may affect the discoveries. And I mean, I understand the problem with black boxes.
Yes.
An experiment, it is a black box actually, but my answer is if there's some control over it, yes. Or is there a way to tackle this kind of problem, or
by the way,
bias?
Yeah, I like a lot, you know, this comparison with the black box and experiment. Sometimes people say, no, yeah, it's completely different, it's not true. But indeed, it's true. Also in experiment, if when you do the experiment, you don't have a controlled environment, right, the results of your experiments are bullshit. A lot of the experiments is to create an environment where you are handling only with the variables that you would like to measure, and you take away all the noise, as clean as possible, etc., etc. Same thing is here. You know, you definitely have to have a way to check the quality, the bias of your data, right? And there is technology that allow you to do it, indeed. So if you want to build a model that has to have an outcome, you have to be super careful on the data selection. But if you want to do the next step, that is what I was telling you before, simply do a brute force things if you are able to learn something from the world. Yeah? You don't have to take away any data. Because the world is that, with that complexity. So what I would like to get is understand if this complexity with this bias, of course, correlate in some way or emerge in some way or not. So you need to know what you do, and you need to know that once you have done, you create your models, maybe the model give you some correlation that is not real. Maybe you have done the models only on a male population and not a female population. Of course, you have a big bias there on the health, for example, right? So you need to know what you are doing, but there are certain applications that have an uncontrolled use of the data as a first step to find if there is some emerging application is what you need to do. Because if you don't do it, it's like if you impose already the answer. And sometimes that is not what you want to have, right? For example, what you are doing in CERN, this QML, is not that you have a set of data that is done in a certain way, you use that data. If then there is something crazy, you analyze a posteriori, but it's not that you throw away data because you want to push things in a certain direction.
At the same time, if I may add, data do drive the result.
Yes.
If we keep on saying that our data are so private that nobody has to have them, and so all machines will work on American data, will perfect drugs and therapeutics for American citizens, their crazy diet, etc., and they will not be good for us. So there has to be an equilibrium there.
But that is why I said that what we are pushing, what I'm pushing personally, is this idea that the base models needs to be done in the open and collaboratively by the largest, broadest set of people, countries, scientists, etc., etc. The advantage is what you said, plus you do this only once. Otherwise, you get to a situation that people are going to redo the same models with a lot of compute power, CO2 emission, blah, blah, to get to the same result. The idea is you develop this scientifically in a pre-competitive way, and then any company, any scientist can take that model, add his own new or proprietary data to come out with a novel outcome. That is where we have to go. So when we are saying open science needs to become the way we are doing science in the next century, that is real. Otherwise, let's go and do something else.
So yeah, I had a very related question, so it's already partially answered. But just to add, in a lot of fields, we're not only limited by biases in the data, we also have errors either in the data or in the simulator. A lot of the stuff that we do, for example, is based on training on simulated data, but our simulator has errors that we don't really understand. Everybody's simulators have errors that we don't understand. And so creating a robust generative model, and robust in the sense that, it works on the laws of physics and ignores the errors in the numerical errors themselves, is a huge challenge. And so I guess I was wondering if you had any thoughts on that.
Look, it's you are completely right. It depends how you do things, but the field of this new generation of machine learning and AI is moving so fast that as soon you have, for example, that question, people already come up with an answer. For example, I was mentioning that we have done this model for fluid dynamics. Yeah. So there, you don't use a transformer, okay? You use a different type of model that allow you to integrate first data simulated on a 3D grid, okay, from the simulation. But then, once you have the model, that can be biased, can be partially not correct, and so on and so forth. You apply this model on a real environment, and you specialize or refine the models with data coming from experiments run, for example, on a car that is really running, and the sensor don't need to be on the grid points because these neural operators are able to work in the continuous, right? So are able to integrate this new, fully clean exact data in the model. So you start with like a perturbation 0, right? And then you put a perturbation 1 with the data, and more data you push in, you are going in the direction that you want. And you can use the same model for a car, for the emission of a jet. The base thing is the same. And then you refine with good data that are in your environment, are coming from experiment, okay? And probably are able to correct the failures of the model itself that you have used at the beginning. So you can do this, many of these things today. Oh, I was not believing at any of the things. I am a computational scientist. I spent 30 years of my life to try to use hybrid simulation and all the type, multi-level, simulation based on differential equations to solve problems. And How many real problems I solved in all my life using this type of things? I don't know, maybe half, okay? And then you get with this new approach and you see that everything was a problem before for this outcome-oriented type of research is solved. And I could not believe myself. So now, when I go to supercomputing conferences, and I will still say people that are trying to use scale molecular dynamics simulation and say, what are you doing? This doesn't work. It will never work. There are different approaches that for the same input, they get a better outcome. So it's the world of simulation, especially the world of simulation is changing. And it's changing for the good, in my opinion, not for the bad.
A very, very significant statement here. One more question from me, which is kind of on the side. Okay, you talked us very efficiently and motivated us a lot about artificial intelligence and its ability even to generate models. I would like to have a comment from you on the energy cost of all this.
So we go back to what I was saying at the beginning. Of course, you have two ways to evolve this field. Number one, you decide that you want to create a single model that integrates all the data and all the modalities, okay? And then you use this model to solve any problems that you do have. That one will probably allow to bring many discoveries because you connect data of different modalities in different environments so you understand, but is going to be hugely expensive, especially when you use it. People say, when you train. Yes, when you train, you do once. When you use 1 million of time. And if you have to use 1,000 trillion parameter models simply to give have an answer where I have to go out dinner this evening, you understand that it makes no sense. You use something like this for a stupid question, right? So that is one way to do. Don't forget that the energy and the energy needs to train a model doesn't scale linearly with respect to the model size. Is at least quadratically, okay? And if you only saying this, you should understand that the other way is going to be much better. What is the other way? Instead you do a model with 1,000 trillion parameters, you do 100 models, each of them, with 10 or 1 trillion parameters that are specialized in tasks or modalities or use cases. And then you use an orchestrator on top that, by the way, can be another AI models, where people are speaking about agentic AI, that once you have a question, is going to call the single models and integrate a posteriori. It's clear that, n plus m plus l, blah, 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 at the square here, the square is going to be smaller than the full things at the square, right? So definitely, if you do things right, you can get results that are order of magnitudes with 1 order of magnitude less energy and also more accurate. Because what people are calling hallucination in language, will be also in science. If you put everything together, these models are not clever. These models are only learning sequences that can be of different type of data and predict what is going to be the next step of the sequence based on the previous one. Or if you have a sequence, you take one piece of data, is able to predict what is missing on the basis of that. That is what these models are doing, right? So if you mix things, too many things that are completely uncorrelated, the models can give you answers that are completely no sense. I give this example. Recipes. Recipes is in chemistry, is in the kitchen, is in pharma, is in the process. You can get to a situation, you said, which meal I should cook for my mother-in-law this evening? And the machine say, the best one is a cake with arsenic. Okay? Not because it wants to kill the mother-in-law, but a recipe is a recipe. A chemical or a kitchen, the machine is not able to understand the difference. It depends only on the statistical weight. If there are more data on the kitchen, it's going probably to give an answer that is a food. If there are more data that is chemistry, it gives and mixes things together. So,
thank you very much. So I think we have an opportunity to continue our chat with our guest, with some drinks in Sala del Priore. Therefore, we thank you very much for this very inspiring colloquium. Thank you very much.